In this class, we're going to talk about waves and sound. First, mechanical wave. Mechanical wave is a tangible wave that is much easier to understand because we can observe it and relate. So that's a good point that connects what we learn about the mechanical motions and also the electromagnetic waves, which is not visible and we need equipment to detect. So we start with mechanical waves. So wave have property that you are expected to know and understand. Just like oscillations, they have frequency, wavelength. What's new about waves is the speed. So speed has a relation that equals to frequency multiplied by the wavelength. Every property must be in the SI base unit. So wave motion, for example, this is a water drop that causes these ripples on the surface of water. So this mechanical oscillation spreading out like in ripples in water, that's what we call mechanical wave. Wave has amplitude. That is how much the oscillation of each particle in the media is called amplitude. A wave has frequency that is the same frequency as the oscillation frequency. Wavelength is new. So wavelength means along the direction of the wave propagation, the distance between two same motion of oscillation, that is wavelength. And speed is how fast the wave spreads out. And here we have an example you can look at. Wavelength can be observed in the physics experiment. So we can see actual oscillations of a string. For example, music instruments like guitar strings, they actually have a physical oscillation that can be observed in the lab. Speed of light is the same as the speed of any electromagnetic radiation. In vacuum, the number is 3.0 times 10 to the 8th meters per second. And this is absolutely what human has observed as the universal speed limit. Sound. Sound is a wave that's called a longitudinal wave. That means sound needs a media to propagate. In vacuum, there is no sound. When astronauts are in the spaceships, because there's no air, they cannot talk like we humans do on the surface of the Earth. Sound depends on the medium. So when we talk, it's the air in front of us and between us and other people that will keep a compressed and relax so that that creates the sound. So the air molecules vibrate in between the two speakers, mouth and ear will actually carry the sound. We also have infrasound and ultrasound. Ultrasound test is an important medical examination. And wavelength, frequency, and period of sound is related in the same way any wave speed is related to the frequency and the wavelength. That is the speed equals the frequency multiplied by the wavelength. So here we see like both sound and electromagnetic radiations have speed. However, they have different frequencies and different speed. Electromagnetic radiations have a lot higher frequencies and it has higher speed. And sound has lower frequencies and lower speed relatively. Speed of sound is also depending on the density of the material. Unlike electromagnetic radiations that we're going to learn later, or you might use it naturally anyway, such as our Wi-Fi and our cell phone signals. Sound is a mechanical wave. So the electromagnetic radiation can propagate with no media. In other words, they can propagate, they can travel in vacuum, such as sunlight go through what is primarily vacuum and reach the surface of the earth. However, sound always needs a media. And this media, the denser the media is, the faster sound travels. That is why sound travels faster on train tracks than in the air. In movies, you might see that sometimes people press ear on the train tracks to hear if there's a train coming because sound will go along the train track faster. Intensity and sound level. This is important for the health of our hearing. Our human can hear sound because we have little pieces of bones in our ear that can catch the vibration and pass that signal to our brains. So the louder the sound is, the stronger the vibration is. And the stronger the vibration, the more it causes these bones to vibrate. Like I said, because these bones are delicate, very strong sound can actually cause damage to our hearing by causing a lot of wear and tear in these bones. So sound intensity is something we monitor to ensure hearing health and safety. So sound intensity is measured by decibels, and it's the power in watts over the area in meters, and also it's a log function. So waves. So here are some pictures of waves. First is a stationary wave. If we throw a pebble into the lake, then the water ripple just spreads out on the stationary water. And also the other one is a boat. The boat is moving, so the wave will actually follow the boat in different directions. So when a car approaches to you, oh no, a car is leaving from you, going away farther from you, they actually sound differently. So this is what we call the Doppler effect. When the car is approaching, it sounds with a high pitch sound. When the car is going away from you, it sounds more low pitch. So when the car is moving, from how the sound frequency changes, we can actually detect which direction it can move. So this is a valid way for us to determine the direction of an object moving by analyzing the sound it sends out. So this is what we call the Doppler effect. In this equation, the frequency zero is the sound's natural frequency in the air that's stationary or at rest. The velocity is the velocity of the sound, and V0 is the velocity of the object moving. So when they're moving toward each other, frequency shift down. And when the two moves away from each other, it becomes frequency becomes smaller. When the two moves towards each other, the frequency becomes a higher pitch. So this is what we call the Doppler effect that we usually have heard this many times, and this is just the theory underneath that explains it. A shock wave. So if the object goes faster than the sound, that creates a shock wave. A shock wave can be extremely loud, and that sometimes can be damaging. So that's why we actually limit how fast airplanes fly usually, because to prevent creating a lot of shock waves. And standing waves. Musical instruments sounds very pleasing because they have harmonic sound, and that is because standing waves can be achieved by carefully designing the length and tension in the string in the musical instruments. And also the length and the shape of woodwind instruments. And standing waves has a wavelength So standing waves, the length of these musical instruments are multiples of their natural wavelength. And so here are examples. The first harmonic is when the length of the instrument is the length of half a wavelength. And the second harmonic is when the length of the instrument is exactly the length of the wavelength. And third harmonic is when the length of the instrument is 3/2 of the wavelength. And the fourth harmonic is the length is 4 times. When musicians or technicians adjust the tension in the string, they also adjust the wavelength. So this is in summary, we went through what's frequency, wavelength, speed, intensity of waves, and sound is a special type of wave. Sound is easier to observe and it's mechanical. We can also hear it ourselves, so it's a tangible wave that we study in this case. It's also an important connection between the mechanical oscillations and waves that's very tangible that we can study to the electromagnetic waves that is not as tangible, but we are going to study. So that's why we make sure we always do hands-on experiments with waves and sound. And this will establish a important connection and also help us do better with the whenever we need to understand anything about electromagnetic radiations or waves, such as Wi-Fi signals, cell phone signals, etc.